Hi, I'm David Sloan. I'm the scientific lead on the Physics of Fine-Tuning project here in Oxford, and with me today is Luke Barnes from the University of Sydney, who's an expert on all things fine-tuning. So we're going to have a discussion about our thoughts and ideas and directions in fine-tuning.
Very good. Thanks for having me here.
All right, so Luke, you've written several papers and in fact writing a book on issues of fine-tuning. So what is fine-tuning to you?
So for me, fine-tuning is something that comes up when you try and test a theory to find out whether it's true. So you have some idea about how the world works. And often when we write down, say, an equation that's supposed to describe how nature works, there's free parameters in that. They might be in the equation itself, saying, you know, how massive a particle is or how strongly it interacts with other things in the universe, or they might be the initial conditions that you need. You know, your equation tells you how the world changes, but you then need to tell it how the world starts off, and then it will tell you what happens next. So if you have that free parameter, you have a number in there, you don't know what it is, you have to go out and measure it. This is all fine, but occasionally we find out that if that number had been slightly different from what we measure it to be, the world would be an extremely different place. In particular, so it wouldn't look anything like this. So there's all sorts of strange things you can do to the world by tweaking these parameters. But fine-tuning in particular is it then makes, because that parameter is an unknown, it's just an assumption in your theory. If it has a suspiciously precise value, then you start to get suspicious of the theory. It only explains the data we have when you make a very precise assumption about something you don't know. And that's the physics definition of fine-tuning. It's broader than anything to do with life, although this issue's come up with life in particular. So if you have a theory, so an example that we use in the book is, suppose that you see a burglar entering a building, you have the CCTV footage, and they walk up to the gate and they put in the 12-digit code and the door opens and in they go. And you think about, how did they manage to do that? So if you have the theory that they just guessed the code, well, there's a trillion possible codes, only one of them gets in. So that theory would have to make, if you think about it in these sorts of terms, there's all sorts of ways to see what's wrong with the theory that they just guessed the code. But if you think of it in these ways, there's a suspicious assumption in there that the code that they guessed just happened to be the code that got them in. And so if you have a physical theory that's trying to explain the world, and which doesn't explain the value of its parameters, if it needs a suspiciously precise value or in particular some sort of coincidence between different values to explain the world, then we get a bit suspicious.
So taking your example of a code, you would somehow sort of think the level of precision, say in terms of the number of digits that you needed of a parameter,
right,
would be an idea of how fine-tuned that is.
Yeah.
And so you're saying that if this number has to be precise at 10 or, for example, 12 digits long, then it's not an explanation of anything that would require somewhat less information then, or?
Right, so you can think of it as, in the burglary case, you think of it as sort of an opportunity for a different theory to come in and explain the data better. So the theory that it's an inside job, someone gave the burglar the code, there's some sort of conspiracy going on. So fine-tuning in itself doesn't prove anything as such. If there's an alternative theory we think that could explain the data, then we've got some sort of reason to think that, so fine-tuning, I guess you could say, is a excuse to go and look for a theory which doesn't have this fine-tuned property to it. Maybe you can't find it. There's all sorts of cases in the history of physics of people trying to explain the exact values of constants. We can talk about those. There are an awful lot of dead ends that we've run down. But there's also been the success stories that what we thought of as a free parameter, someone's explained it in terms of some deeper physics to explain why it is. But the fine-tuning then was sort of a clue pointing, here's this parameter, there's something a bit fishy going on here. Look for a theory which will enlighten what's going on here.
So what you're saying is that fine-tuning isn't itself a sort of a goal or an endpoint for a theory. But you say it's an indication that we need to sort of look a bit deeper, we should look for something more fundamental and try from there to explain the theory.
An actual example from physics comes from the theory of inflation. So in the very early universe, there's the actual density of the universe, and there's the density that's called the critical density between when the universe, well, if it's matter dominated, recollapses or expands forever, between the different flat versus curved geometries. So you have those two numbers, and from what we can tell in our very early universe, those two are equal to each other to one party, and well, it depends how early you say, but at least one party in 10 to the sort of 16, and if we can push right back, it's one party in 10 to the 60. So there's no deeper reason in our models why they should be the same, because these are just initial conditions. So I mean, they're just put in by hand in the standard cosmological model, and so that's a clue to go looking for something else. So hence we have a theory of inflation, where in the very, very early universe, before all of that, there's a period of expansion which will drive these two numbers towards each other. And then you think, okay, now we understand why we prefer that theory of inflation to the pure, we just assume the values of these numbers, because we feel like we've got an explanation for why those two numbers are the same. Now there's a lot of assumptions that go into that sort of argument, but that's the basic outline of it.
So what you're outlining there is really sort of the flatness issue with inflation.
Yeah, so this is called the flatness problem, yeah.
But, I mean, there is an alternative explanation for this, right? And that is that the universe is just flat. You know, if k is equal to 0 in your Friedman models, this parameter is precisely 0. It doesn't need to be tuned to 1 part in 10 to the 60.
Right, but I mean, there's an alternative explanation of the burglar case, which is the burglar just guessed the code right. That doesn't do away with all the other alternatives. It seems like, and actually this is an assumption that has been challenged by a few people, but it seems like pick an early time in the universe could have whatever density it likes, you just put more or less matter in. Why would it have exactly the critical density? If you're just picking a density, you know, just pick whatever you like. But for some reason ours is, you know, straight on, you know, within ridiculous precision of this critical density. And that seems like a fact about the universe which could be explained. It's a clue. Maybe we do have to say at the end of the day, if there was no good theory, alternative theory to explain this, maybe at the end of the day we would just say, okay, that's just how the universe started. But at least, you know, certainly in the history of physics, it was, as they discussed the flatness problem in the late 70s, I think it was, this spurred the theoretical work of the pioneers of inflation in the sort of late 70s, early 80s. They went looking for a theory precisely for these reasons.
But again, in these cases, this is specifically related to a closed universe. So, this relates to the topology of the universe. Right. If the universe is topologically flat, which would be a valid explanation, suppose your quantum theory of gravity just predicts topologically flat manifolds for some reason. Right. That would be a perfectly valid explanation.
Yeah. So one of the ways this has been challenged is there's been various calculations, which I can't explain in any easy way, saying that actually in the set of possibilities, we shouldn't say that they're all equally likely. The way of looking at them, the possibilities, which respects, you know, the theory of Einstein's theory of gravity, all these sorts of things, and the sort of the way it should measure these different possibilities, you should consider it almost certain that there will be a flat universe. This critical density, the coincidence we have, and if that's true, then we made an assumption in our fine-tuning calculation that was wrong, and we've learned something then about the universe. So, you know, if you do a calculation of a probability and you get a very small probability, as we seem to get with the flatness case fine-tuning, it tells you that if, you know, maybe something unlikely happened, sure, there's just something unlikely that happened. Or one of the assumptions you made in getting to that probability was wrong and you need to go back and revise it. It could be, if inflation is true, it's the assumption that these are just initial conditions, whereas actually they're not initial conditions. There was something before them that drove the universe towards this initial state. Or it could be this assumption that all the densities are equally likely, whereas these arguments say, no, the critical density is almost certain when you look at it in the right way.
Yeah, so this sort of brings you into issues of what the measure of this set of possible universes or possible states is, right? So, I mean, in inflation, this is the measure problem of at least classical inflation.
Yeah.
So you gave a very nice example with, someone punching in a code, because you can very easily, sort of using high school maths, calculate the probabilities there. It's just 1 over n to the number of digits or whatever for the length. But in the case of inflationary cosmologies, flatness, these curvatures and so forth, how do you sort of assign probabilities to these events?
So the general case there is quite difficult. Once you've got infinities, let's pick a number. What's the chances that it's an even number? Pick a whole number. 1, 2, 3, 4, 5, 6. What's the chances it's an even number? It seems like the answer to that should be a half. But if you just rearrange the numbers, you can make that probability be whatever you want. What you can do in the burglar case, which is why it's so nice, you're just counting possibilities. But if you've got a continuum or you've got an infinite number, then you're in a bit of trouble. My opinion on this is starting to be that if there really was an in principle problem here with a certain theory, that it couldn't produce the probabilities we need to test it, then that's just a reason to reject the theory. It just becomes untestable. So the onus is on the theory to produce probabilities in a reasonable way. So if all these ideas about infinite multiverses and inflation, which while this expansion happens supposedly in some models, the universe fragments into different domains that might have different physics. If at the end of the day you can't have probabilities of, okay, what's the probability we would observe a universe with galaxies in it? If you can't produce that, then your theory just isn't really a theory at all. Now, in detail how you do that, there's a number of approaches. A lot of the ones most used in the literature try to confine the universe to to consider a finite piece of the universe. So the way you deal with these infinities is you cut out a finite piece of the universe. So for example, there's a horizon around us, so nothing moves faster than the speed of light. So there's a limit to the things out there that could possibly influence me now, or even possibly influence me infinitely far into the future. Cut that bit out of the universe. It's called the causal horizon measure, something like that. Cut that bit out of the universe and just consider that bit, and do all your calculations there, and hopefully things are finite enough that you can get an answer to this problem. But whether that works is an interesting question. Whether there's other ideas about how to do that is kind of interesting. But there's no doubt there are cases where infinities completely ruin any chance of testing a theory.
Yeah, I mean, this is certainly the case of inflation, right? Where when you look at the set of models, there is definitely a parameter, the scale factor, which can go from 0 to infinity quite freely.
Right.
Of course, this isn't a physical parameter. The scale factor itself isn't observable in these cases. So, I mean, it's gauge, and we try and project over it or something.
Yeah.
But nonetheless, the way in which you impose a cutoff on this will actually affect the probabilities you get out.
Yeah.
And so, this causes massive issues. But this sort of brings to a deeper question, though, which is that you say there are these parameters that can have infinite ranges. But is there anything sort of physical that could have an infinite range? Because when you look at these things, they always tend to be things that are, in some sense, gauge, that have infinite range. So, I mean, taking the scale factor example, right? We can always project down to a set of states described by scale factor 1 today, for example, which is what cosmologists normally do. In that case, you sort of get rid of the infinity, and you just want to set your measure on a set of physical observables.
Right.
Do you think there are actually cases where there is a physical observable which is unrestricted in that way?
Well, there's a couple of issues there. I mean, the general issue of could there be infinities in the actual universe is an interesting one. But in fine tuning, the issue is, so I have this parameter. What if there was, what if it could go from 0 to infinity, and I'm supposed to be calculating probabilities on this? I seem to have a bit of a problem. If I think that, my ignorance is represented by, each little range of this number is equally likely, well, you can't calculate probabilities like that. They're all supposed to add up to 1, but there's an infinite number, so that's never going to happen. So I think we can split this into two cases. And it was quite nice. We had a workshop yesterday, and John Peacock was talking. I think he proposed this idea as well. There seem to be two cases here. If you have a constant which doesn't have dimensions, so there's a lot of those in physics. So if you decide you want to measure in feet rather than meters, this constant doesn't change. Those, yes, they might have an infinite range, but there's no reason to think that every equally spaced region in that range is equally likely, because we think that a constant they should be of order 1. So 1 seems like the natural number for a dimensionless constant. So there are a huge number of calculations you can do in physics where it's called dimensional analysis, where you know the relevant quantities in a problem, and what you need is the equation that relates these quantities. And if you're a little bit lucky, or if you've got a particularly simple model, there turns out to be only one way to put them together, which makes sense in terms of the dimensions. So you couldn't have a case where one side of the equation was measured in meters and the other side in seconds. And actually, that seemingly simple idea nails down the form of the equation. And so we think that if we did the proper calculation, we'd have the same form, but there'd be a number out the front. So there might be all these other quantities around, but there'd be a dimensionless number out the front. And from sort of doing a lot of these things, that number turns out to be usually of order 1. So it'll involve geometric factors like pi, there might be e and 2, but they're equally likely to be multiplied or divided, so the 1 is the usual sort of size of these things. If that's the case, then an infinite range of a dimensionless parameter is not really a problem, because you can just make it peak at 1. There's a range of shapes of that function which will allow you to add the whole thing up to 1 to have a normalizable probability out to infinity. And the other case is a dimensional constant, but those are usually something to do with mass, or a mass to the power of something. In which case you have a strong upper limit from what's called the Planck scale. There's a very sort of naive calculation you can do in just sort of super gluing quantum mechanics and gravity together. If you had a single particle which had this Planck mass, and it's actually quite small, it's 10 to the minus, it's measured in fractions of a gram. But if one particle had that mass, and you do this naive calculation, it turns out it would sort of become its own black hole. Now, we don't have a quantum theory of gravity. And so a particle is very much a quantum thing, and a black hole is very much a gravity thing. And so if you've got a single particle that's a black hole, you need that theory of quantum gravity. So that limit there, the Planck mass, is the limit of our ignorance. Beyond here, we just don't know what's going on. And so that gives you the sort of finite range. You shouldn't give, even if you gave everything a sort of equal measure, you shouldn't start giving measure out beyond the Planck mass, because you have no idea what's going on out there, including mass might not make any sense. I mean, there's all sorts of crazy theories about what's going on when you put quantum mechanics and gravity together. Time, space, energy, all of those things might not make sense either. So you could just say, all right, you're equally likely between 0 and the Planck mass. So I think there's a way around these infinities. Again, if there was a theory which really hit a problem with these, I think that would just rule it out as a testable theory.
So I think there's sort of something very interesting here. So you're saying you can use the Planck mass, for example, as a cutoff, and so in your sort of meta theory in which you have these dimensionful constants, but for some factor of order 1, say, in front of them. Once we wipe out all the constants using C and H bar and G and all these things, we should be left with something dimensionless. And you say that should be of order 1, right? Yet, a fine-tuning issue could be, for example, that this number has to be precisely 1.00. Suppose I had 1 plus 10 to the minus 60.
Right.
I'd still argue that that was a fine-tuned parameter.
Yeah, sure. So in that case, the issue is that the range is very small. So it's close to the natural value, but there's still only a very small range in which it explains the value of, it explains whatever it is we're trying to explain. In the case of life, it would be, you have to be in that range in order to have a universe which permits life, by which we don't, we have no idea really how life formed in the first place, ask a biologist. But what we really mean is the sort of physical complexity, the physical structures upon which life relies. So a small change and you obliterate the periodic table. We don't know how life formed chemically, but there must be some sort of chemistry for life to form at all. So in that case, yes, we're close to what seems like a natural value, but there's still a range there that's very small. And it's an opportunity then. So if a dimensionless number, if we knew it to be between 0.25 and 0.75, and there was another theory, there was a theory which said this thing's just a free parameter, it's a dimensionless parameter, it could be anything, it could be roughly 1, and our observations say it's between 0.25 and 0.75. And there's another theory which says it's not a free parameter, it's definitely 0.5. Then it's not totally clear whether we'd prefer one of those over the other. Depends how ad hoc the calculation of the 0.5 was, whether that seemed to be just put in by hand. But if a better experiment then comes along and suddenly this 0.25 to 0.75 shrinks down to 0.5 plus or minus 0.00001, suddenly that theory which predicted a half is looking great because of that fine-tuning issue. Now the free parameter theory looks fine-tuned, and the one where it's not a free parameter theory looks like it's nailed it. It's predicted the lottery win. It should be rewarded for this wonderful prediction.